Before I start this video, I want to let you know that this could be quite taxing because we are guessing a lot and the process itself could take some time, so pay close attention. If we have an nth degree polynomial, we are going to have a whole lot of roots, or zeros. They could be rational, they could be irrational, or they could be complex. So complex zeros are non-real zeros, obviously. The rational and irrational ones are real zeros. So one of the tests that we use to determine a rational zero is to guess. Now, guessing is not the best way to go about it, but with higher order polynomials, it is advised that we guess. And the process is quite easy. First, we list out all the factors of the constant term. Then we list out the factors of the leading coefficient, and we divide the factors of the constant by the factors of the leading coefficient. Once we get this, we can use synthetic division to find the other zeros, and eventually, at times, we may have to use the quadratic formula to get to the zeros. So we'll start with an example. So here, all we want to do is list all the possible zeros. So that is the constant term, and that would be the leading coefficient. So the factors of the leading coefficient, which is 1, are plus or minus 1. Why? 1 times 1 is 1, and negative 1 times negative 1 is also 1. The constant term, which is 10, has the factors plus or minus 1, plus or minus 2, and plus or minus 5. Because 2 times 5 is 10, negative 2 times negative 5 is also 10. And once we list out all the factors, what we do is divide the factors of the constant by the factors of the leading coefficient. So we have plus or minus 1 divided by plus or minus 1, plus or minus 2 divided by plus or minus 2, and plus or minus 5 divided by plus or minus 5. So if you divide plus or minus by plus or minus, you'd still get plus or minus. So plus or minus 1. Sorry, I kind of jumped the gun here. I'm going to go back. So it is plus or minus 1 divided by plus or minus 1, plus or minus 2 divided by plus or minus 1, plus or minus 5 divided by plus or minus 1. And if we divide plus or minus by plus or minus, we'd still get plus or minus. So plus or minus 1, plus or minus 2, and plus or minus 5. We have to keep in mind that these are the possible rational zeros. At times, you may try all of them, and you may find out that, oh, none of them are rational zeros. It could happen if we end up having non-real zeros. In other words, we have complex zeros. So all we are trying to do here is list the possible rational zeros. So that doesn't imply that every single one of them here would be a zero. So in a similar manner, here the constant term is minus 3, and the leading coefficient is 4. So the factors of the leading coefficient are plus or minus 1 and plus or minus 4. The factors of the constant are plus or minus 1 and plus or minus 3. So we start dividing. Plus or minus 1 divided by plus or minus 1, plus or minus 3 divided by plus or minus 1, plus or minus 1 divided by plus or minus 4, plus or minus 3 divided by plus or minus 4. So we would end up getting plus or minus 1, plus or minus 3, plus or minus 1 over 4, and plus or minus 3 over 4. So those are all the possible zeros. So we want to find the zeros of this polynomial. So we start with the constant term, which is negative 20. And the leading coefficient is 1. So the factors of 1 are plus or minus 1. For 20, we have plus or minus 1, plus or minus 4, and plus or minus 5. So the possible roots are plus or minus 1 divided by plus or minus 1, plus or minus 4 divided by plus or minus 1, plus or minus 5 divided by plus or minus 1. This would mean the possible roots are all zeros are plus or minus 1, plus or minus 4, and plus or minus 5. So we should always start simple. So the simplest one is plus or minus 1. So let us test. If we plug in one of the zeros, the function has to become zeros, and one of the possible zeros, then the function has to become 0, and if it becomes 0, then it is an actual 0. So I'm going to plug in 1, so 1 cubed plus 8 times 1 squared plus 11 times 1 minus 20. That would give me 1 plus 8 plus 11 minus 20, which is 20 minus 20, 0. So right away I got the actual 0, which would imply x minus 1 is a factor. The reason being, if I set x minus 1 equal to 0, I will get x is equal to 1, which is one of the zeros that we guessed. So now that we have x is equal to 1 as a 0 and x minus 1 here is a factor, I am going to simply divide using synthetic division the polynomial 1, 8, 11, negative 20 by 1. So we bring 1 down. 1 times 1 is 1. We add 1 times 9 is 9. And then 20. 1 times 20 is 20, which would give us 0 when we add. This would imply that we are left with x squared plus 9x plus 20, and this is a quadratic equation that can be factored, so we could factor it as x plus 5 times x plus 4. So we set x plus 5 times x plus 4 equal to 0 and solve for the zeros. This would mean x plus 5 is 0 and x plus 4 is 0, indicating that x minus 5 is a 0 and x is equal to negative 5 and x is equal to negative 4. This would imply the zeros are 1, negative 4 and negative 5. we use the same process to find the zeros of this polynomial, x cubed plus x squared minus 5x minus 2. So the constant term is minus 2. The leading coefficient is 1. So the factors of the leading coefficient are plus or minus 1. And for the constant, we have plus or minus 1 and plus or minus 2. So the possible zeros are plus or minus 1 divided by plus or minus 1, plus or minus 2 divided by plus or minus 1. So the possible values are plus or minus 1 and plus or minus 2. So we start simple again. Let us start with 1. Let's start with negative 1. So negative 1 cubed plus negative 1 squared minus 5 times negative 1 and negative 2, which gives us negative 1 plus 1 plus 5 minus 2, which gives us 3. So clearly that is not a 0. So now we plug in 1. So that would give us 1 cubed plus 1 squared minus 5 times 1 minus 2, which is 2 minus 5 minus 2. We get negative 5. So that is not a 0. Let's plug in 2. 2 cubed plus 2 squared minus 5 times 2 minus 2, 8 plus 4 minus 10 minus 2. We have 12 minus 12. We get 0, so check. So we've got our first 0. This would imply x is equal to 2 is a 0, which would mean x minus 2 is a factor. So we can divide the polynomial by the factor to find the other zeros. So what we have here is 1, 1, minus 5, and minus 2. We are dividing it by 2, and using synthetic division, 1 comes down here, 2 times 1 is 2, 1 plus 2 is 3, 2 plus 3 is 6, 6 minus 5 is 1, 2 times 1 is 2, and we get 0. So what we have now, the leftover polynomial is x squared plus 3x plus 1. So that is the quotient at the end of synthetic division. So we have to set this equal to 0 and solve for x. Could we factor x squared plus 3x plus 1? It doesn't look like it. So let's use quadratic formula. So minus b plus or minus b squared minus 4 times a times c divided by 2a. So minus 3 plus or minus square root of 9 minus 4 divided by 2, so minus 3 plus or minus square root of 5 over 2, so the roots are minus 3 plus root 5 over 2 and minus 3 minus root 5 over 2. So the zeros of the polynomial are x is equal to 2, minus 3 plus square root of 5 over 2, and minus 3 minus square root of 5 over 2. And things are getting harder. So the constant term in this polynomial is 13. The leading term is 1, or the leading coefficient. And luckily, what we have is a prime number. So the factors are plus or minus 1 and plus or minus 13. The leading coefficient would have factors plus or minus 1. So the possible zeros are plus or minus 1 over plus or minus 1, plus or minus 13 over plus or minus 13. We end up getting plus or minus 1 and plus or minus 13. So we always start simple. So let's start with 1. So f of 1, f is that function over there. It's 1 raised 4 minus 6 times 1 cubed plus 22 times 1 squared minus 30 times 1 plus 13, which is negative 5 plus 22 minus 30 and plus 13, 17 minus 30 plus 13, which is 0. So we got lucky. So the 0 is 1. This would imply x minus 1 is a factor. Now we go about dividing the given polynomial, which is 1 minus 6, 22 minus 30 and 13. 1 goes in there, 1 comes down, 1 times 1 is 1. We have negative 5. 1 times negative 5 is negative 5. 22 minus 5 is 17. 17 times 1 is 17. And negative 30 plus 17 is negative 13. 1 times negative 13 is negative 13. We add and we end up getting 0. So this would imply x cubed minus 5x squared plus 17x minus 13 is the quotient. So here we have to set x cubed minus 5x squared plus 17x minus 13 equal to 0 and solve for x. Now we can't jump to the quadratic formula right away because the polynomial here is a third degree polynomial. So the degree here is 3. So we can use the rational 0 test one more time, and if we look at it, the leading coefficient is 1. The constant term is negative 13. So the factors are plus or minus 1 and plus or minus 13. So the possible roots or possible zeros are plus or minus 1 and plus or minus 13. Let us start simple again. So let's start with f of 1. Mind you, this time we are going to plug the value 1 in that function right there, because we've moved on from the original polynomial to the reduced one. So when we plug in 1, we have 1 cubed minus 5 times 1 squared plus 17 times 1 minus 13. 1 minus 5 is minus 4 plus 17 minus 13, which is 13 minus 13, we get 0. So got lucky again. What are the chances? So now we've found the next 0, which is 1 also. So x minus 1 is a factor because x is equal to 1 is a 0. So we do synthetic division again, and this has to be in the reduced polynomial, which is right here. So we have 1 minus 5, 17, and minus 13. So 1 goes in there because x minus 1 is a factor. So 1 comes down. 1 times 1 is 1. Negative 5 plus 1 is negative 4. 1 times negative 4 is negative 4. 17 minus 4 is 13. 1 times 13 is 13. And when we add, we get 0. So the quotient here is x squared minus 4x plus 13 equals 0. Now, could we factor this? We cannot, because 13 is a prime number. So let us go ahead and use quadratic formula. So minus b, minus of minus 4, plus or minus square root of b squared minus 4 times a times c, divided by 2a. So we have 4 plus or minus square root of 16 minus 52, which would give us 4 plus or minus square root of negative 36 over 2. So here, when I bring the negative 1 out of the square root, I get I. So square root of 36 over 2. And square root of 36 is 6. And I have a 2 in common, so I would cancel out the 2's. I'd end up getting 2 plus or minus 3i. So the roots are x is equal to 1, 1, 2 plus 3i, and 2 minus 3i. It is important to know that anytime you have a complex root, they would always occur in pairs. What do I mean by that? So here we have 2 plus 3i. We ended up getting 2 minus 3i. Those are complex conjugates of each other. So if you know that there is one complex root, there has to be another complex root, and that would be a complex conjugate of the root or the complex root that you just found. So the pointer over here simply reiterates what I mentioned. So if you have a complex root, the other root has to be complex, and it has to be a complex conjugate. So for every complex root, there has to be a conjugate root. For every complex zero root, they mean one and the same, just to avoid confusion. So 0 root, they are the same. If you have 1 0 that is complex, there has to be a conjugate. complex conjugate, which would also be a 0. Do not forget that. So here we have a third degree, nth degree polynomial with real coefficients, and the degree is 3. They have told us that 3 and I are zeros, and f of 2 is 20. So 3 is a 0, that is a given, which would imply x minus 3 is a factor. I is a 0, but I is not a 0. Well, that was a bad joke. So x minus I is a factor. Here is the key thing. Since I is complex, its conjugate must also be a 0, since we have plus I minus I is its conjugate. So those two are complex conjugates. That would mean x plus I is a factor. So now that we have the factors, the polynomial is f of x excuse me, equal to some constant c multiplied by x minus 3, x minus I, and x plus I. So c times x minus 3 times, if we FOIL those, we have x minus x squared minus ix plus ix plus 1, because I squared is negative 1. So those two would go away, and we will have c times x minus 3 times x squared plus 1. So this would mean the polynomial is c times x minus 3 times x squared plus 1. If we find c, we are done. So what is c? We are given that f of 2 is 20. So this would mean c times 2 minus 3 times 2 squared plus 1 must equal 20. So c times negative 1 times 5 equals 20, which would imply c is 20 over negative 5, which is negative 4. Therefore, f of x has to be negative 4 times x minus 3 times x squared plus 1. You can leave it as is, or you could FOIL and write it as a polynomial. So let's try that. 4 times x cubed plus x minus 3x squared minus 3. Distribute the 4. We have negative 4x cubed, negative 4x, plus 12x squared, plus 12. Put things in order. Negative 4x cubed, plus 12x squared, minus 4x, plus 12. And that is our third degree polynomial. So here in example 6, we have a fourth degree polynomial that we have to find because n is 4. The zeros are I and 3i. So I is a 0, which would imply x minus I is a factor. And its conjugate has to appear, so negative I is also a 0, which would imply x plus I is a factor. 3i is a 0, that is given, which would imply x minus 3i is a factor. minus 3i is a 0. It has to be. So x plus 3i is a factor. So here, those two are complex conjugates, and those two are complex conjugates. So the polynomial is x plus I times x minus I times x minus 3i times x plus 3i, and do not forget the constant c in the front. So if we FOIL the first two factors, we would end up getting x squared plus 1. If we FOIL the last two factors, we would have x squared plus 9. So we found f of x, and we know f of negative 1 is 20. Excuse me. So c times x squared plus 1 times x squared plus 9 would equal 20. Plug in negative 1 for x, negative 1 squared plus 1 times negative 1 squared plus 9 equals 20. So c times 1 plus 1 would be 2, negative 1 squared is 1, 9 plus 1 is 10, equals 20, which would mean 20c equals 20, so c is 1. So the polynomial that we found is f of x equals 1. I'm plugging in the value of c in here, and x squared plus 1 times x squared plus 9. We could leave it as is or write it as a fourth degree polynomial. So x raised 4 plus 9x squared plus x squared plus 9, which would be x raised 4 plus 10x squared plus 9. So here is our last case. We have to find all zeros of this polynomial x cubed minus 5x squared plus 17x minus 13. So the leading coefficient is 1, and the constant term is negative 13, which would imply its factors are plus or minus 13. The factors of the leading coefficient is plus or minus 1. This would mean the possible zeros, all roots, they mean one and the same, are plus or minus 13 over plus or minus 1 and plus or minus 1 itself. So those are the possible zeros. Let's start simple. Let's start with negative 1. So negative 1 cubed, negative 5 times negative 1 squared, plus 17 times negative 1 minus 13. We have negative 1, negative 5 times 1, negative 17, negative 13, negative 6, negative 17, and negative 13, we get negative 26, so that is not a zero. Let's try positive 1. 1 cubed minus 5 times 1 squared plus 17 times 1 minus 13, which is 1 minus 5 plus 17 minus 13. 17 minus 5 is 12, 12 plus 1 is 13, 13 minus 13 is 0, so we found our first zero. So the first zero is 1, right here. is a 0, which would imply x minus 1 is a factor. Since we know that x minus 1 is a factor, we can use synthetic division to find the other zeros. So 1, minus 5, 17, and minus 13. Those are the coefficients in the original polynomial here. So 1 goes in there, we drop that 1. 1 times 1 is 1, so 1 goes up there, add negative 4. 1 times negative 4 is negative 4, add 17 minus 4 is 13. 1 times 13 is 13, we add, and we end up getting 0. So that leaves us with the quotient term, x squared minus 4x plus 13. So we set x squared minus 4x plus 13 equals 0, and we solve for x. So could we factor it? We cannot. We could use quadratic formula, so minus of minus 4 plus or minus square root of minus 4 squared minus 4 times a times c divided by 2 times a. So 4 plus or minus, looks like we've done this problem already. So we did it early today, so this was a waste of time. So divided by 2, so 4 plus or minus square root of negative 36 over 2. When negative 1 comes out, we have I square root of 36 over 2. Square root of 36 is 6 over 2, so we have 2 plus or minus 3i. Or perhaps not. We didn't do this problem. Oh, we did. It's right here. So if you look at the cube or the cubic polynomial here, right there, it's the same as the last one here, which is why I've recognized it. Again, if you notice, the roots are complex and they occur in conjugate pairs. So the zeros or the roots are 1, 2 plus 3i, and 2 minus 3i.